Welcome back to Advent of Code 2017. We're on to problem 11, almost halfway. So that's good. Hex ed. That's my kind of education. Hex ed. Right. Crossing the bridge, you've barely reached the other side of the stream when a program comes up to you, clearly in distress. "It's my child process," she says. "He's gotten lost in an infinite grid." Oh. Okay. Fortunately for you, you have plenty of experience with infinite grids. Unfortunately for you, it's a hex grid. Why is that unfortunate? I like hex grids. Alright. The hexes in this grid, are aligned such that adjacent hexes can be found to the north, northeast, southeast, south, southwest, and northwest. You have the path the child process took. Starting where he started, you need to determine the fewest number of steps required to reach him. A step means to move from the hex you are to any adjacent hex. Okay. Fine. These are the steps we take. So this is just using... what's it called? Hexagonal grids, using one of these coordinate systems. Let's go with the one that's usually recommended, which is... the axial coordinate system, I think. So... yeah. Okay. I have all I need to start. Okay, so the input is that. All right, so we want moves, let's say moves equals that. Okay. Are they comma separated? Yeah, okay. All right, so start equals, let's say, all right, so we want start Q, start R equals 0, 0. For move in moves, So we need a delta map. So it maps. So we've got to take each of these. So let's have a look. Have a look at the grid. So we want to map northeast to +1, -1. And similarly, we just want okay, so we've got northeast 1 -1, east 1 0, southeast 0 1. Then there's southwest -1 1. West -1 0. And then northwest got 0 -1. So that's basically the axial system. It's just useful because then you can do stuff with it easily. Okay, so we extract the delta and then start Q plus equal dq start R plus equal delta R. And then after all this is terminated, we just want to know the distance we are from 0. And the formula for this is hello 16-bit hyperturbo. And also Arakis, thanks for the follow. Doing some Python coding. We're doing a hex grid. That's fun. So when you have a hexagonal grid, all right, that's cool. 16-bit. Yeah, I decided to code because I'm actually processing my video from the Halo run, which I finished yesterday. So I can't really play any games because it's using up most of my CPU. Waiting for that to finish, it might take a couple of hours. Arakis, I'm day 1 advent of code, I'm using TypeScript. It's day 1 as in what? Day 1 of 2015 or the very first one? What was the first one? Or day 1 of 2017, the one I'm doing now? 2022. Okay, yeah, I did that one live. Yeah. Honestly, after going back and doing these earlier ones, I thought the recent ones were actually quite tough. Like 2022, 2020, there were some really tough problems there. But I went back and did 2015 and 16, and there was not as much tough stuff in there, so it got harder over the years. So is this the training software? I'm not sure what you mean by training software, but it's not really a training software. No, it's a, let me show you the, actually I could just switch the window here. So it's a website called Advent of Code, and it has a bunch of each year in December, in the 25 days leading up to Christmas, they release one problem a day, And it's basically a kind of, it's aimed at all levels, so even beginners in programming can kind of attempt this. The problems start really easy and they get harder as you go along. So, you know, to get to the end, you'd probably need to know some mathematics and some kind of advanced data structure stuff. But to do the first few, it's just like, you know, take a list of, I don't know, fruits being sold in a shop and sort them by price and give me the maximum 3, something like that. It's just stuff that you can approach as a beginner coder. Of course, you'd still need to know coding, but so yeah, I'm up to day 11 in 2017. We had a couple of hard ones. 10 was pretty hard. This was a cryptographic one. Very long description. Very long. Wow, was it that long? It really was. That was tough, actually. Well, it wasn't actually tough. It was just it was really tough to interpret the description. Once you get what it wasn't too tough. But and then what else? Yeah, this one was hard as well, but they haven't been too bad so far this year, 2017. So now we're walking around on a hexagonal grid, and the first problem doesn't seem that difficult. Basically, they say we're on a hexagonal grid, we're starting at 0, 0, and they're giving us a series of moves: west, southwest, southwest, southeast, so on. So we move those steps on the hexagonal grid. And then the question is, how far are we from the beginning in terms of number of steps? It's not as easy as on a rectangular grid because we know how to find distance on a rectangular grid. You take the horizontal distance plus the vertical distance, but it's not quite that trivial on a hexagonal grid because you have a less trivial coordinate system, or at least there are various different coordinate systems you could use, and they all are non-trivial in their own way. But I'm using this one here called axial coordinates, basically. And I'm trying to find the distance now. What is it? Here we are, distances. Axial coordinates. That's the formula there they're giving us. Okay. Let's just copy that in then and change it to Python. Oh, I didn't have the window up. Well, doesn't matter now. Oh, I did, okay. So that is not in Python though. So let's call it norm, because you're finding the normalized vector of some position in the hexagonal grid. We're going to return abs. We don't need all these excessive parentheses. Actually, we did. So it'll be z dot q z. Actually, we don't need z in front of that. Just say if we're given a q and an r, those are the two parameters describing the position in a hexagonal grid. Then we take the q minus 0 So it simplifies to that if we put all the zeros in there. That's it, that's the formula. And then we just print the norm of where we are standing. I don't know, let's try that. Key error S. Oh, it's not capitals. Hang on. They're trying to move south? Oh. This is not the... Oh, this is... There's two ways you could organize these hexagons. You could have the flat bit at the top, or you could have the pointy bit at the top. And they've done it with the flat bit at the top, which means... Our coordinate system is slightly off. Okay, we can fix this. We just say rotate everything a bit. So there's a north. In our hexagon, there isn't a north. There was a northeast. So if we rotate everything a bit to the anti-clockwise direction, so change northeast to north, change east to northeast. Keep southeast, there's no east. Hang on, let me just look at the... So it goes north, northeast, southeast, south. North, northeast, southeast, south. Southwest, northwest. Southwest, northwest. Alright, let's do it like that. So everything's rotated, so it doesn't matter. 685. Correct. Okay, so we can trust this website that they've got the correct formula there. All right, part 2. How many steps away is the furthest he ever got from his starting position? That's so easy. Well, such an easy part 2. We just keep track of the furthest we've been every step. So, okay. So that was part 1. Part 2. So we say, as we go along, furthest equals 0. And we say, as we go along, furthest equals max of whatever the previous furthest was, and the current norm of start Q start. I don't like calling it start Q start R because it's not actually the start. We're modifying it. So can we just call that Q and R? Q, Q, R, R, Q, R. Part 2, print furthest. Don't do about. Stop. Run. Norm is not defined. 1457. So they've gone as far as 1457, but they came back to 685. That's plausible. That's it. Okay, that was a bit easier than I was expecting. I mean, there's way more complicated things you could do with a hexagonal grid. They basically did the single most easiest thing that you could really come up with, which is find the distance between these 2 points in the hexagonal grid. Like, there's way more they could have done. Got all this stuff. Finding intersections between convex subsets. Path finding through a maze in hexagonal grids. Rotating, I don't even know what that's doing. Reflecting. Rings. Spirals. Field of view. So this is like video game stuff, like seeing what things you can see and what things you can't. Good for board games. Hex to pixel. Pixel to hex. Wraparound maps. Okay, I'm having too much fun here. Let's carry on with the problems. Alright, now we have to actually ask ChatGPT to solve it and see if he can solve it faster than we can. And he normally does, so. So I ask him, can you write a Python program to solve the following problem? And then I just paste it as is. All right. And he's done it, I think. Okay, so he's gone for the cube coordinates instead of the axial coordinates. That's fine. That's also acceptable. Probably makes it easier to calculate the distance. It just means you're using 3 coordinates instead of 2, and I would say one of them is redundant. So you're using more space overall, which I would not like to do. Okay. Hang on, but he's not handled the input correctly. Oh, but they didn't say. They did say. We have to tell him that the input is. Okay. This should work for comma separated now instead of new line separated. Okay. They did say in the problem, so but it's alright. I'll let ChatGPT off in that case. All right, let's test it. $1,505? That's wrong. Way off. Oh. What did he get wrong? Why is he computing the max distance? I didn't ask him to do that. He's cutting corners here. And it's not even the correct answer if that was the question. Interesting. I don't see anything. Okay, pretend he's trying to find the max distance. Oh, he is trying to get the distance, not the max distance. What's he done wrong then? Interesting. Alright, well, anyway, we can't help him solve it. We just have to say, you got it wrong. Please fix. I don't see much change here. $685. Yeah, that's correct. Okay. Thing is, I didn't make any mistakes. I got it right first time. He got it right second time. So who wins in this case? He did solve it faster than I did, though, even with the mishap. I never really established a rule set here. I think I'm just gonna have to go with what I've been doing so far, which is just whoever gets to the correct answer fastest, even if you're making mistakes. Because that's really how the website measures your success. They don't care if you make mistakes, as long as you get the answer in the end. Alright, so ChatGPT still wins, I guess. I haven't given him part 2. It looks correct. One, 4, 5, 7. Yep, correct. Okay. All right. Well. ChatGPT wins, as always. All right, next problem. So on to day 12. Digital plumber. Walking along the memory banks of the stream, you find a small village that is experiencing a little confusion. Some programs can't communicate with each other. Programs in this village communicate using a fixed system of pipes. Messages are passed between programs using these pipes, but most programs aren't connected to each other directly. Instead, programs pass messages between each other until the message reaches the intended recipient. Okay. I worked on a system like this once for it was like a company that was trying to prevent flooding. So they had lots of stationary flood detectors around the city, and the flood detectors would send the message to other nearby flood detectors. to get it back to the main hub. So if the water knocked down one or two of them, the message could still kind of get across. For some reason though, some of these messages aren't ever reaching their intended recipient, and the programs suspect that some pipes are missing. They would like you to investigate. Okay. You walk through the village and record the ID of each program and the IDs with which it can communicate directly. Each program has one or more programs with which it can communicate, and these pipes are bidirectional. Sure. You need to figure out how many programs are in the group that contains program ID 0. Ooh, it's like topological, what's it called? Connected set problem. Yeah, it's just a connected set problem. So we start from 0, we do breadth first search. Keep searching every little path until we found everything we can, and that is just normal BFS. Alright, easy peasy. I've done this a million times, but I bet I'll get it wrong. I don't like this format, but fine, we can deal with this. No, don't paste that. So we want class graph define init. So we want to have there's no empties here. Every single integer has connected integers. Okay. That's fine then. Is that a fact? Doesn't really say in the problem, but it seems to be from the input, so. Okay, so self.edges, should we say neighbors? Neighbors equals that. So to add an edge between U and V, that means we take self.neighbors U hang on. Let's just import default ticks, that makes things easier. So it's bidirectional. So U is a neighbor of V, V is a neighbor of U. Get connected component. Can't think of a shorter way to phrase that. All right, so let's make sure we can populate this. So we've got a G equals graph for, okay, so now we want to go line by line. For line dot strip. No. Line in f dot read lines. So we. Okay, we can say neighbors equals line dot strip dot split on this set of characters here. So that will give us, the left part will just be the integer, the right part will be this thing here. Okay. Cast that to an int. Turn this into list of integers. Okay, and then for neighbor in neighbors, g dot add edge from you to that neighbor. Okay, so by the end of this, we should have a bunch of neighbors in G. From collections, 0 maps to 1774 and 199. Yep, that's correct. Okay. Now, we need to fill in this bit here. So, given. Okay, so Q is just an empty list containing the starting point, U. Visited equals empty set. So while the Q has stuff in it, current equals Q dot pop. For any neighbor in G dot in self dot neighbors centered on current, if neighbor not in visited, if it hasn't been visited yet, then put it in the queue. Mark that as visited. That's it. And then we return visited. So what was the original question? How many programs contain 0? Okay. How many programs are in the group containing 0? I assume including 0. Yeah. Okay. So print the length of this G dot connected component 0. That's it. 175. Correct. Part 2. There are more programs than just the ones in the group containing program 0. The rest of them have no way of reaching that group, and still might have no way of reaching each other. A group is a collection of programs that can all communicate via pipes, either directly or indirectly. The programs you identified just a moment ago are all part of the same group. Now, they would like you to determine the total number of groups. How many groups are there is what they're asking. Okay. Fine. We just do this thing we have repeatedly until we've found every group. So we say checked equals just an empty set. To be checked is the set of g dot neighbors dot keys. So this is all possible vertices, while to be checked I always forget, how do you extract something from a set? Well, this is the hacky way of doing it. It's not efficient, but x equals list to be checked 0th element. I don't like doing that because it rebuilds a huge list every time you're doing that. There is a way to, you need to write your custom iterator to get something out of a set. Peek at something in the set. I don't know if there's a clean way of doing that, but just do this, whatever. X equals that. Oh, groups. So X equals that. C equals G dot get connected component of X. So we pick something that hasn't been checked yet. Find the connected component centered on that that's connected to X. Remove that from to be checked. We don't even why we don't even need this variable here checked. We just need to be checked. And add 1. And this should just keep going until there's nothing left to be checked with. Two, 1, 3 groups. Yeah, okay. That makes sense because the degree is like 2 to 3 most of the time, so you would expect quite a few groups. 2, 1, 3. Correct. All right, that was just a warm-up BFS. Find a connected component. Find all connected components on the most generic graph they could come up with, which is just a bunch of vertices which are connected to each other bidirectionally. So oh yeah, I gotta do ChatGPT. I think this is the last year I'll do the ChatGPT thing for, because it was interesting at first, but now it's not. We know ChatGPT is beating me in all these problems, so I think we've established that we don't need to test it anymore. I'll do it to the end of this, but I don't think it's as interesting as it once was. Like, we get it. ChatGPT's replacing us programmers. All right. Okay. It's given us something. $175, correct. He's using an actual queue. I just used a list. It's actually, I think mine was actually more efficient. No need to use a heap or anything. Just use the stack. Standard array. No, is it 213? Yeah, it was 213. Yep, okay. You win. $13. Packet scanners. You need to cross a vast firewall. The firewall consists of several layers, each with a security scanner that moves back and forth across the layer. To succeed, you must not be detected by a scanner. By studying the firewall briefly, you are able to record in your puzzle input the depth of each layer and the range of the scanning area for the scanner within it, written as depth range. Each layer has a thickness of exactly 1. Okay, a layer at depth 0 begins immediately inside the firewall. Okay, fine. Oh, it's some sort of simulation. Oh, okay. Now, there's probably a fast way and a slow way of doing this. Slow way would be every step we update where S is. Fast way would be to use clever modular arithmetic to know exactly where it is without having to update all these. Your plan is to hitch a ride on a packet about to move through the firewall. The packet will travel along the top of each layer, and it moves at 1 layer per picosecond. Each picosecond, the packet moves 1 layer forward, and then the scanners move 1 step. If there is a scanner at the top of the layer. As your packet enters it, you are caught. If you were to do this in the configuration above, we would get caught immediately, wouldn't we? In this example. So initial state, all the scanners are at the top. And then the scanners. So picosecond 0. We move here. And then the scanners move down. And then we move there. Then they move up. Right, we do get caught though, don't we? You are caught in layer 0 and 6 because your packet entered the layer when its scanner was at the top when you entered it. You are not caught in layer 1 since the scanner moved into the top of the layer once you were already there. The severity of getting caught on a layer is equal to its depth multiplied by its range. So given the details of the firewall you've recorded, if you leave immediately, what is the severity of the whole trip? So yeah, we can work out instantly for each layer when we'll arrive there and whether it will be at the top as we are arriving. That's all we need to know. Interesting problem. Okay, we need to make a method that says, given caught, given a depth, a width, that's it. Will we get caught? All right, let's think. It'll be easier if I use paint for this. Solve by paint. Where's paint? It's a bit bright. Can we Okay, so let's think. We have layer So we're arriving into this space here. This has a width, let's say W. And it has a depth, D. Hang on, can I put this below that? There we go. Okay. So what time will we arrive at that space? Well, it's D, isn't it? We arrive at time D. If D is 0, we arrive at time 0. Okay. Okay. Where will the scanner, so this is where the scanner is, be at time D? So at time 0, it will be here. Time 1, it'll be here. Time 2, it'll be here. So at time W minus 1, it'll be at the end. Then it comes back. So W, it will be here. So when will it come back here again? W minus 2. Hang on, let me look at the input again. So if it's depth, if it's width, yeah. If it's width 3, okay, yeah. So it will be at the starting point at 0, W minus 2, 2W minus 2, and so on. Wait, does that make sense? No. Something is wrong here, because it doesn't work if W is 1. See, if it's width 1, then it would be 0, 1, 2. It will always be there, right? So 0, 1, 2, 3, so on. But that doesn't match this formula. Have I done something wrong here? So it starts at 0. At 0, it's here. So at 1, it's here. 2, 3. Oh, wait, no. There's a 2 in there. I meant to put 2W minus 2. So this is wrong. I meant 0, 2, W minus 1. So does that fit this? If W is 1, that'll be... That still doesn't work. Wait, what? So if it's just 2 spaces, it'll be at 0, 2, 4, 6, 8, so on. It'll be at the top on those numbers. Why am I getting this wrong? So in this case, that's correct. 0, 2, 4, 6, 8, so on. If W is 2, W minus 1 is 1, so it will be 0, 2, 4, 6. Okay, that's correct. Does it work for W equals 1? It would be 0, 0, 0, 0. What? It doesn't work. So why doesn't that work? I think width 1 is just a special case. We have to have a separate formula for that. It's a bit weird because you don't ever leave. So it's... It takes... Oh, yeah, okay. All right, anyway, back to our formula. So what is the point in all this? Basically, we're saying if our number is a multiple of 2W minus 1, then it's at the top. So that would get caught. All right, that's the formula. It took me a bit longer than it should have to get there. And if W is 1, be 0, so it's sort of vacuously. It's just we handle that separately. Okay. So let's just try and code this then. All right. So court depth width. If width is 1, return true. Else return depth so if we try to divide 2 times W minus 1, it divides evenly. That's it. That's the formula. So for each line, depth width equals int x for x in line dot split. So it's going to be that. If caught, we get caught for that depth and width, then we add, so what did they want us to add? The score we get, the penalty score, is severity, it's called. Depth multiplied by range. I should use the term range, not width. Okay. Right, score plus equal DW, character from Hey Arthur. She always finds her way into algebra somehow. Is that it? Print score? Something feels a bit off about this. Let's just try running it. 1904. Okay, it's correct. Solved by Microsoft Paint. Well, not fully. We did solve one problem this year fully by Microsoft Paint. No coding done whatsoever. I just calculated it all in Microsoft Paint. That was crazy. Problem part 2. Now you need to pass through the firewall without being caught. Easier said than done. You can't control the speed of the packet, but you can delay it any number of picoseconds. For each picosecond you delay the packet before beginning your trip, all security scanners move one step. You're not in the firewall during this time. You don't enter layer 0 until you stop delaying the packet. You just choose one amount of delay. Hacking trick, yeah, exactly. Oh, I thought you can choose to delay at each step, so you can choose to stay where you are, like if you're playing Frogger or something. But no, it seems you just delay at the start. So we need to keep increasing the delay amount until we find a delay amount that would actually not get us caught. Okay, we just keep increasing the delay from 0, 1, 2, 3, and so on. I guess that's not hard. So that was part 1. Part 2. So now we decide to wait X amounts of picoseconds and then just do this whole thing and hope that we can get through all of them without getting caught. The mathematical solution to this is probably using the Chinese remainder theorem or something like that. It usually is. But it's just a few numbers, so we don't need to do something that advanced. We can just try each time value. So let's say for t in... Oh, Python has something like this. What was it? It's called from iter tools import I have to look it up. Infinite sequence is what I want. Just gives you the numbers 0, 1, 2, 3, 4. It's just an easy way of getting them instead of having to write a for loop. Count. It's called count. Let me just check. I want it to start at 0. Does it start at 0 or 1? Yeah, okay, starts at 0. Alright, so starting at 0. We have to adjust this now. We have to assume we've delayed. So this formula works if we haven't delayed. So now we have to put delay into there somewhere. How does it work? So it's as simple as this, isn't it? We just add delay to depth. that would represent the time we arrive at that spot. Let's just put these trying to use the terminology the problem uses. What do they call them? Scanners. They call them scanners. No, layers. They're called layers. So layers equals that. TW. Okay, so given a t value t, if all not caught given a depth, width, and delay t for dw in layers. So that's saying if all of these layers don't catch us at this time with this delay t, then we found our value t and just break. So I don't know how long that'll be. So just leave it running. It probably won't take long. It is taking long. Let's just leave it a while. As you add scanners, the complexity grows because all the scanners are moving. Oh, there we go then. 3,833,504. I thought I was going to have to break out the Chinese remainder theorem. We did have to use that last year, in last year's problem set. Chinese remainder theorem sort of gives you a... It's basically this. Given a set of... It's been ages since I did my A-levels. It's like... Basically this. Given a set of scanners which are all moving according to a set path and a set, like... period. Chinese remainder theorem gives you the time when they're all at zero. The next time when they're all at zero, basically. It's very useful. Well, let's hope this is correct. Okay, it's good. It's correct. All right, ChatGPT. Let's see if ChatGPT uses the Chinese remainder theorem. You probably just Google it and copy it from Wikipedia, and that'll probably work as well. Copy the diagrams in as well. I mean, ChatGPT can interpret diagrams. Will it actually fit? Yeah, it does. Okay. Good luck. Insta-solve. Let's see if it works. Depth. rage -1 times 2. Yeah, I mean, that looks correct. And he didn't even use Microsoft Paint for that one. $1.904, correct, yeah. And now we have to give him this part 2. Oh, he's going for the simulation. No, he's... Oh, no, that is what I did, essentially. I was simulating, but I wasn't actually moving the scanners manually every step. That would take too long, probably. But I was still using the quick method here, the Microsoft Paint solution. Find minimum delay. Delay equals 0. So he just infinitely increases it. Okay, fine. Seems correct. Okay, it's gonna take as long as it took me, so... It was much quicker. I don't know why. Was it more efficient what he's done? I don't think so. I think it's the same. He's done the same thing. I don't think... Maybe mine wasn't short-circuiting. So short-circuiting means... No, it does short-circuit. If it finds a violation amongst these, then it stops calculating at all, moves on to the next one. Maybe all is not actually that efficient, but it's really nice to code it that way. It just looks like natural English. $3833504. 3833504, correct. Okay. Let's see. Should I keep going? It's 8:30. Yeah, I'll go for one last one. Okay. Day 14. So it's... Oh, okay. I need to update that. ChatGPT is on 10. Disk defragmentation. Wait, let's have a look at this. Oh, it looks a bit... do I want to do this? Yeah, go on. All right. Oh, sorry, I don't have the window up. Here we go. There we go. All right. Day 14, disk defragmentation. Suddenly a scheduled job activates the system's disk defragmenter. That's defragmentation. For those who don't remember having to defrag your computer manually, which is always actually a really satisfying process when you looked at the visual thing. I suppose you still actually can do it in Windows, it's just not, there's no reason to manually do this stuff, but I mean, people who know what they're doing probably do. Were the situation different, you might sit and watch it for a while. Oh, what's this? A YouTube video? Oh, this is Windows 95 defrag visualizer. Yeah, this is what I was saying. This was so satisfying to watch. All that efficiency. All those gaps getting filled in. Wait, so, and this was back using 32-bit systems, wasn't it? So 64-bit systems, it's not as big an issue, I think, or maybe I don't know. Can I do it in Windows 10? Oh, you can. Defragment and optimize drives. You can optimize your drives to help your computer run more efficiently. 7 days since last retrim. So Windows has been doing it anyway without me telling it to. I mean, that makes sense. All right, anyway, that's a blast from the past. But today, you just don't have that kind of time. It's soaking up valuable system resources that are needed elsewhere. And so the only option is to help it finish its task as soon as possible. The disk in question consists of a 128 by 128 grid. Each square of the grid is either free or used. On this disk, the state of the grid is tracked by the bits in a sequence of not hashes. Oh, yeah, don't remind me of not hashes. A total of 128 not hashes are calculated, each corresponding to a single row in the grid. Each hash contains 1 to 8 bits, which correspond to individual grid squares. Each bit of a hash indicates whether that square is free, 0, or used, 1. Just look at the input, maybe this will... Huh? Oh, the input is this word here. Okay, the hash inputs are a key string, a dash, and a number from 0 to 127 corresponding to the row. Okay, so given this string, we add a dash. I prefer to call it a hyphen because technically dash is a different character from hyphen, but these days it's all just hyphen. Dash is longer, but it's not even on keyboards anymore. Or is it this one? Yeah. No, that's underscore. Yeah, no, keyboards don't even have dash anymore. It's just a bit longer than a hyphen. I don't know what it was used for. But I mean, when you work in software programming, there's all kinds of redundant software that's using stuff from the 80s and 90s. So you still have to be aware of these weird things. For example, if your key string was this, then the first row would be given by the bits of the not hash of that. The second row from the bits of the not hash of that. And so on until the last row. That. Okay. So we're supposed to use the not hash program we wrote before. Okay. I can do that, but... ...32 hexadecimal digits. Each of these digits correspond to 4 bits. total of 4 times 32 equals 128 bits. Turn each hexadecimal digit to its equivalent binary value, high bit first. 0 becomes 000 and 1 becomes 1. Okay. Given your actual keystring, how many squares are used? Okay. We just need to import the method from before, but... So this is 10 from before. Well, I didn't really make this nice and neat, did I? I'm just having a look at problem 10. What exactly was the not hash? The not hash was the final output. Huh. Okay, so we need to... Oh my god, alright, so... What did the input look like for that? For problem 10? There's a bunch of characters. It looks like comma separated integers, but then part 2 revealed we actually interpret them as characters. Okay. So okay, so we need to make a method called not hash. So we have to copy some of this stuff. So we have a not round. I don't remember this stuff. It's going to be hard to... Okay. So... So first, we extract a bunch of lengths. So we take the orange character for Carol and S. Do we still add these numbers? Yeah, let's have a look. I don't know. I don't think they're being clear enough here. So, how many characters would we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to 12. I don't think adding the extra characters, the extra lengths they added, told us to add, is part of the not hash algorithm. So take that out, I think. Or maybe we do, I don't know. We'll just leave it in for now. So define not round. Okay, so got the lengths. We define these. N is what? N is 256. All right, we have to take that out. Okay. Then what? Okay, so we've got the not round, we've defined that. Hang on, no, we're going from here. So 0, 0. Correct. And then we do that, which in our method translates to replacing current skip size with that. Okay, then what? So then we work out the dense hash. God, didn't think we'd have to be returning to this. We need to import reduce. Don't print anything, this is gonna not hash equals that. Return that. So that whole thing should take a string and turn it to a not hash. So let's test this. Print not hash of, so the example they gave was They don't even give an example, because how do we know we're using... I'll have to figure this out later. Alright, so... Alright, so then so we know how to compute a hash of a string. The output of a not hash... Let's go back to this. So we're here now. The output of a not hash is traditionally represented by 32 hexadecimal digits. Is that what we've got? Let's try running it. Yeah. Okay. Each of these digits corresponds to 4 bits for a total of 4 times 32 equals 128 bits. To convert to bits, turn each hexadecimal digit to its equivalent binary value. Fine. Hello, Zavi boy. Have you done Advent of Code? Can you try my Advent of Code clone? You've made an Advent of Code clone, like a website? I'll have a look at it. I won't be able to do it this stream because this is the last problem I'm doing, and then I'm done for today. Yeah, you can put your URL in the chat. I'm happy to have a look at it. Probably not now though. Just finishing off this one, so this is a weird problem. Okay, so we have a hash, we have a string of 32 digits. Okay, we just want to convert hexadecimal to binary. How do we do that? Convert hexadecimal to binary. Use bin. That makes sense. It's bin 6. Bin. You just put it straight in. Oh yeah, that makes sense. Okay. So for for character in okay. For character in H, B equals bin of character. So that will give us, I'm gonna have to print this. I don't know what these things look like. 4 digits, right? It'll give us 4 digits. So let's say bin string equals that. Bin string dot append b. And after we do that, let's just print string. I want to see what this looks like. Also, I want to use the same example they had, so it's going to be 0. Like that. Okay, let's try that. String object cannot be interpreted as integer. Oh, I'm supposed to interpret, do something with bytes. I don't know. Binary. Int hex string 16. Okay, so it's int of that base 16. Damn it. We need pad. How do you pad with zeros again? You do dot zfill 4. Yeah. Result equals okay, so that gives us the final output. Now we just need to say from 0 to 127. So for I in range 128, we do all of this. We say equals that plus the string value of I. Total equals 0. And we want to count how many ones there are. How many squares are used? And used means 1. Yeah, we want to count how many ones there are. Total plus equal result dot count 1. Print total. What a mess. Run that. Get 8108. That is for the seed that we start with. It's that. No. It's going to be seed plus, so it'll be hyphen plus the number. All right, if this all is correct, 8108, we should get the same. We got the same number as the example. That can't be coincidence. Okay, fine. See, the thing that I think was ambiguous is whether you do this stupid thing here. You add these 5 random numbers which don't mean anything that they gave us in problem 10. They said, okay, take whatever's the input, but put these 5 numbers at the end. Specifically 17, 31, 73, 47, 23. I wasn't sure if in this problem we still need to add those 5 numbers because it's just not clear from the description, but apparently we do, so. Now we just change the input to be R's. 8216. Come on. I want to be done with these not hashes. Okay, we're on to part 2 though. Now all the defragmenter needs to know is the number of regions. Now what? A region is a group of used squares that are all adjacent, not including diagonals. Every used square is in exactly one region. Lone used squares form their own isolated regions, while several adjacent squares all count as a single region. The following 9 regions are visible, each marked with a distinct digit. Okay, it's connectivity. We can use the algorithm from before. Of particular interest is the region marked 8. While it does not appear contiguous in this small view, all of the squares marked 8 are connected. Yeah, okay. So they're combining problem 10 and problem 13. That's quite cool, actually. Right, well, we're not done. So now we've got... So we need to make a grid. That's part 1. Grid equals that. Grid and result. Part 2. So basically we have to copy this stuff we've done in 13. No, not 13. 12. Okay. So basically we want to do this. Groups equals 0. To be checked is an empty set. And for I in range 1 to 8, for j in range 1 to 8, to be checked to add ij. So every one of these coordinates needs to be checked. So we start with 0 groups. While there are still things that need checking, we take one of them, we find the connected component of x. We haven't written that method yet, and then we print the final group's value. So the last thing we need to do now is define connected component. Okay, and this, we can kind of copy what we've done before, but now we need to adjust it a bit. So the queue starts with x. Visited is that set there. Ooh, there was a mistake. We should have added 12. That was actually a mistake. Didn't seem to be a big deal, but it was. It would actually give a wrong answer. No. It would give a wrong answer if you have an isolated group of 1. What would happen? I think it just happens to give the right answer, but I don't like what it's doing. Alright, so anyway, we'll fix it back there. We'll say visitor.add you. There we go. Okay. Alright, so q equals x, visitor equals set, visitor.add x, while q, ij equals q.pop. Now, we need to find all neighbors. So for di in -1, 0, 1, for dj in -1, 0, 1, neighbor I, neighbor j equals I plus di, j plus dj. If neighbor I, neighbor... Right, first of all, if di, dj is 0, 0, just skip this one because that's redundant. In fact, we'll just keep going in circles. So we found a neighbor. No. It's using up, down, left, right adjacency. Okay, so we can't do it like this. Instead, we have to say for neighbor in, so it's -1, 0, 1, 0, 0, -1, 0, 1. 4 neighbors. Neighbor I, neighbor j equals I plus di, j plus dj. All right. Now we do the range check. We say if 0 is less than or equal to neighbor I is less than 28 and 0 is less than or equal to neighbor j is less than 128. Okay, carry on. Then we found a valid neighbor. So, but we also have to check. Oh yeah, this to be checked, it has to be only ones. If grid I j is 1. To be checked. Okay. All right, now we've got a neighbor. If grid neighbor I, neighbor j is 1, that's a connected neighbor. And the last thing is just make sure it's not already visited. If neighbor not in visited, we put it in visited. And pop it in the queue. Right, that is one hefty nested for loop. And just return visited. That should work. Run it. Grid IJ is 1. Oh, sorry, it's... Huh? Alright, gotta print grid, see what it looks like. Okay, that looks like zeros and ones to me. This string index out of range. Can we make sure the length is correct? One, two, eight, one, two. Oh god, why is there 1, 2, 4? What's going on? It's all kinds of different sizes. Zfill should guarantee that. What does Zfill do again? I don't think I'm doing this binary thing correct. Let's have a look. 0B. Okay. Oh, I've got it back to front, haven't I? We need least significant digit to the right, which is not, which is, hang on, no, we're doing it correctly. That is what we've got. Let's see. So 0 becomes 0000, 1 becomes 0001, E becomes 1110, F becomes 1111. I've got the count right, but why is... Okay, just try printing all that, see what happens. This should always be width 4, right? Maybe the problem then is... What? Even 0 is handled correctly, okay. So... if length h not equal to 32, print h. If length b, just take this one out. What? These are not length 32. What's going on here? Should they be padded with zeros? Let's have a look again. Maybe we just pad it then with zeros. I don't know what happened. Maybe, yeah, maybe that's the issue. Dot z pad z fill, I mean 32. So maybe we lost some zeros at the front because of the way I did it. Okay. Got the right numbers. Neighbor is not defined. Neighbor. I neighbor J. It's not being visited. Then we add that and that. 1033, that's the final number. Alright. Don't feel so confident. Nope, it's too low. So let's... Are we still getting 8216 as the total? Yes, we are. So we're getting the first part correct, but this grid... Alright, let's try the example. This is not going to help us much, but... So in the example, we should get 1242. The example used the phrase... that one. Oh, 1 second, I just need to check something. What the? Whoops, I just opened up a video, sorry. Okay. So try this example. It's going to be wrong, isn't it? But it doesn't tell us much. One, one, two, three is what we're getting for the example. And they say it should be 1, 2, 4, 2. Damn it. All right. What could be going wrong? So we're getting the correct number of ones. It's a bit worrying that our hashes are... So is it correct that we're padding it with zeros? I don't know. No, no, it shouldn't be, should it? Why did the zeros get missed from the front? It's just a string. Hang on. So zeros are missing somewhere. We need to find out where we're getting rid of them and put them back. We can't just add them at the front. It's not necessarily being lost from the front. Take that out. So somewhere in our algorithm we had a mistake. Reduce lambda, so that gives us, I don't know, some number. So dense hash should have 16 things in it. Here's the problem. Try printing dense hash. Take that out. So this was a problem with our previous program. It's just they weren't really testing for this. So it looks like that. Those are integers. So if we do hex z for z in dense hash, try that. Damn it. What does that look like? Ah, sometimes it's only one character. So here we just have to do dot z add 2. It's one character, we add one more. It might be 0, in which case we still just add one more. Try that now. Z fill, why do I keep adding z pad? Well, okay, that probably works now. So z fill, so down here, put that in, it shouldn't flag. Perfect. Okay. 1242. Is that the correct answer? Yes! Okay, now switch back to our problem. This should work now. If this doesn't work, that doesn't make any sense. Because it's just a hash change, so... 1139. Oof. Okay. Okay, let's see if ChatGPT can do this. I'm gonna be harsh on ChatGPT now. If he gets it wrong a couple of times, I'm like, okay, you lose. I gotta be harsher. Oh. How are we gonna do this? Because ChatGPT doesn't know the not hash. Okay, ChatGPT is probably going to lose this. So let's see if there's a way we can actually communicate this to him, because he needs to know how to do the previous problem. So oh my god, okay. This probably won't work. So we need... We don't have an input this time. The input string is that. All right, and then first we have to paste the actual problem. Note that the not hash algorithm is defined in the following problem. I don't know if we can even paste all this. So we're not going to be able to paste all this. Also, we're going to have to take these out, these prompts, because I don't want him answering them. Alright, that whole thing. I think he'll fail. Like, what the heck? No way. He's probably figured it out. I'm not going to give him many second chances here. So that is the problem. One big description. Alright, we'll just try it then. Oh, he might actually have solved it. 14. Func tools. import functors. Number of square used 64. No. Okay, I'm not giving him a second chance. It's a mess. What is he doing anyway? Zfill. He's using Zfill at least. That's something I failed to do the first time. He is actually adding the weird 5 numbers. That's correct. All right, we will actually give him a second chance. Let's wrong answer. 64 is too low. What was the correct answer? 8216. I mean, it looks like pretty good code. It's just probably a very minor issue somewhere. Did I... It looks like exactly the same code. Nope, there's no way he's solving that. It's too long. All right, that's a win for me. And that is day 14. All right, enough. Please don't give us an extension problem from day 14, like continuing this not hash thing. I mean, I like the concept, but I mean, it's been a couple of days since I did problem 10, and if you think about it, in the actual live December of this, it would be 4 days since you last did that problem 10, which is even more than 2 days. So of course everyone's going to have forgotten how that worked, and you kind of need you did actually need to know the inner workings of your algorithm for problem 10, because you needed to adjust it from 14. And I needed to even debug it, and you may not have even solved problem 10. So it was a kind of a rough problem to give people, but it's fair. I mean, it's not unreasonable. It's just tough. So if we look at, there was a drop in 14. Oh, I'm not looking at the... Yeah, there was a drop in submissions, correct submissions for 14, clearly. Not by much, but there was a drop. It was difficult. I would expect more of a drop. Let's have a look at the leaderboard for 14. Both stars in 5 minutes. Crazy. Whatever. And this was before ChatGPT was invented, which was public at least. All right, that's it for today. Getting there. So next time we're 15. So we are more than halfway through. And now it just gets harder and harder. But they're good problems. The not hash thing, it's alright, but it's not actually that hard. It's just reading a load of description and just doing step by step. They're not, the individual steps are not that hard. It's just a lot to unpack. I quite liked the packet scanners was good. Digital plumber was just a warm-up. That was too basic BFS. Hex ed, I was excited when it was a hex grid, but then the problem was actually a bit too easy. Literally just computing distance between 2 points. That's too basic. Yeah. Okay then. So Yep, next time I'll carry on from day 15. All right. See you next time.